Acceleration is any change in velocity in a given time. Remember that velocity is both speed and direction. And so if it's a change in speed or a change in direction, it can be a change in velocity, and so it would be acceleration. What we're going to focus on here is called linear acceleration. Linear acceleration is only looking at that change in speed, and that's what we'll look at for our calculations here. A stands for acceleration, and it will be measured in meters per second squared. That squared is important in your units here. You won't do anything to the number with that, but it identifies an acceleration. Your V's are both velocities. Your VI is your initial velocity, and your VF is your final velocity. We use V for the variable because the most important part is that we're measuring a velocity. The final and initial tell you where it is. And then T stands for time, and that is measured in seconds. Velocities will be measured in meters per second. When we take meters per second and divide by seconds again, we're left with meters per second squared. Again, we have our variables here. Acceleration, again, is measured in meters per second squared. Velocity is meters per second. Both velocities are meters per second, and time is seconds. How might this look in a calculation? Here's an example. A dog accelerates at 5.1 meters per second squared for 1.2 seconds. If it starts at 2.1 meters per second, how fast is it going after accelerating? So that would be our VF. Let's look at the variables we have here. 5.1 meters per second squared. Anytime is meters per second squared, that's our acceleration. So we write A equals 5.1 meters per second squared. 1.2 seconds is a time. So we would say T equals 1.2 seconds. I would highly suggest writing SEC for seconds. Sometimes if you just put S, you'll read it later as a 5 and calculate incorrectly. It starts at 2.1 meters per second. So VI equals 2.1 meters per second, and VF is what we're looking for. Well, the equation that we have is A equals VF minus VI divided by T. We actually are solving for VF in this equation. So we're looking for VF here. And so we need to rearrange accordingly. The first thing we need to do is not have any fractions. And so we'll take and we'll multiply both sides by T. Right now it's VF minus VI divided by T. The opposite is multiplying. So in doing so, I end up removing that and bringing it to the other side. Now I have T times A equals VF minus VI. I'm still trying to get VF by itself, and so I need to do the opposite of what's happening to the VI. Right now VI is being subtracted. The opposite of that is adding it. So I'll add it to both sides. VI, if I take it away and give it back, it cancels it out. But I do that to both sides, VI, like that. By canceling these out, I'm left with VF on this side. So I have VF is equal to VI plus T times A. I'm just putting that in parentheses so we can separate it a little bit. Now I have my numbers. My VI is here at 2.1 meters per second. So I can say VI equals 2.1 meters per second plus, I'll take my T of 1.2 times my A of 5.1. If you're not sure what numbers go where, pay attention to what your variables are, and you can match them up within the equation. So now I can take my calculator and say 2.1 plus, and I'll put the parentheses in here, say 1.2 times 5.1, parentheses again, and it ends up with 8.22, and we say meters per second. So VI, sorry, these are VFs, VF, I had it there we go. VF, what our final velocity is, ends up being 8.22 meters per second. What that tells us, looking at the problem as a whole, it accelerated at 5.1 meters per second squared for 1.2 seconds, and it started at 2.1 meters per second. So it's 2.1 meters per second, it accelerates for that amount of time, and after it has accelerated, now it's going at 8.22 meters per second.